So now I'm going to discuss two very important ideas when it comes to linear transformations and functions. And this is the ideas of one-to-one and onto. They're going to really require us to think about domains and their codomains, okay, and what happens when we actually utilize a linear transformation, okay? So let's first start out by defining what it means to be one-to-one. So a transformation T, V into W, is one-to-one if for all V belonging to V, if T of V1 equals T of V2, then V1 equals V2, okay? And so you're going to have to sit there and think about this a little bit. Basically what this is saying is that if I have over here, okay, I've got T of V1, right? It's only going to go back to one value, right? We can only map it backwards or trace it backwards along T to one V1, okay? If there was another V2 that mapped to T of V1, okay, then this would not be one-to-one if we actually had that, because that would actually be 2-to-1, or sometimes we might have 3-to-1 or 4-to-1, okay? And under a transformation, to be one-to-one, we just want to make sure that for every value that we have over here in the codomain, it maps back to only one value in the domain, okay? So we want to show it to be one-to-one, and there it is. Take, for example, if now we have V2, V2 is going to go to a unique T of V2, okay? And generally we see that as mapping T of V2 backwards. So there's a way of showing, in fact, that a linear transformation T V to W is one-to-one, and that it has that special quality. And that is if and only if the kernel of T equals 0. So this is the perfect way to actually prove that a transformation is in fact one-to-one. Show that the kernel of T equals 0, and we show that in fact the linear transformation is one-to-one. So let's go through and prove it because I think it's kind of handy to help us think about why this is the case. Okay, so suppose T V to W, okay, is one-to-one. Then for all V belonging to V, if T of V equals T of V1 equals T of V2, okay, then V1 equals V2. So now we want to prove that the kernel of T equals 0. So what I'm going to say is that T of 0 equals 0, trivially. We know that that's always true, otherwise we wouldn't have a linear transformation. Okay, then we let V2 belong to V such that T of V2 equals 0. Okay, but T is one-to-one. Since T of 0 equals T of V2, by definition, V2 has to equal 0. Okay, so what we're saying here is this. We've got this definition of what it means to be one-to-one. So we know that for all V, if T of V1 equals T of V2, then V1 equals V2. That means that their inputs are the same. If their outputs are the same, the inputs have to be the same. Okay, that's kind of what we're saying. So what happens here is we say, okay, well, I know T of 0 equals 0. That's trivial. I don't actually have to prove that. I know it's going to be the case because it's a transformation, right? Then I'm just going to say, well, let's have another V that's in V, okay? And we're going to say that V equals 0 or equals the 0 vector when we act on it by the transformation. But since T is one-to-one, that means that V2 equals 0. So, since this is true for all V, then the kernel of T is just going to end up equaling the 0 vector, okay? Because all the vectors within T are going to end up being the 0 vector. Now we want to go the other way around. So suppose that the kernel of T is equal to 0. So it's the 0 vector, okay? And what we'll do is we'll let T of V1 equal T of V2, okay?
then, using just a little subtraction, we're going to get t of v1 minus t of v2 is going to end up equaling 0. Okay? All right? And because t is linear transformation, that's going to also give us that t of v1 minus v2 is going to end up equaling 0. So we kind of bring it inside. All right? Now, because the kernel of t is equal to only the 0 vector, okay, this means v1 minus v2 has to equal the 0 vector, okay? Because the only thing that transforms, that t transforms into the 0 vector is the 0 vector. So v1 minus v2 has to be the 0 vector. Well, what's the upshot of that? Well, that means, thus, v1 equals v2, okay? And that's our definition. We started out with t of v1 equals t of v2, and then we showed that v1 equals v2. So t is 1 to 1. So let's use this. Let's suppose that we have this transformation. It's t of x1, x2, x3, and it goes from t of x1 plus x3, and then x1 minus 2x2 plus 3x3. Okay, and it goes from R3 onto R2. And we want to show is that is not 1 to 1. In order to show that, what we want to do is we want to prove the kernel of t does not equal the 0 vector. Okay? So what I'm going to do is I'm going to actually rewrite this as a matrix. I'm going to get A, okay? A is going to end up equaling, okay, 2, 0, 1, okay, and 1, negative 2, 3, okay? And all I have to do is just look at that that matrix, all right? Look at that matrix, and the matrix there is 2 by 3, okay? So what we have is we are going to have a free variable in ax equals 0. I have too many vectors. There's too many vectors. So the kernel of t does not equal the 0 vector. Hence, t is not 1 to 1. Let's take a look at another transformation. So let's prove that t, R2 to R3, given by t of x equals ax, is 1 to 1. So what I'm going to do is I got a, which is 3, 1, 2, negative 1, 0, 1. Okay, I'm going to show that the kernel of t equals 0. Equals the 0 vector. And that's pretty simply done. We just have to show that ax equals 0, okay, is the trivial solution. And so RREF of A equals 1, 0, 0, 1, 0, 0. And so the kernel of t equals the 0 vector. Okay, what we have there, I mean, if you just go through it, you show kernel of t equals 0 because ax equals 0 has only the trivial solution, given by the fact that we've got a pivot in every one of our columns. Okay, so as the kernel of t equals 0, t is 1 to 1. Now let's talk about a very special set of concepts. And that is how is it that dimension, the dimension of our domain and our codomain, are actually related to being 1 to 1. Okay? So what it has to do with is it has to do with the size of each one of the spaces. First, if the dimension of the range of t is less than or equal to the dimension of w, okay? Let's say, for example, that's the case. By general rank nullity, okay, the dimension of the kernel of t plus the dimension of the range of t is going to equal the dimension of v. If the dimension of w is less than the dimension of v, then the dimension of the range of t is less than the dimension of v. Okay? So then the dimension of v minus the dimension of range of t is going to be greater than 0. Now this statement right here, the dimension of the range of t is going to be less than the dimension of v, is because the range of t is a subset of w. it's within W, okay? So basically, here's the range of T, okay? So there's the range of T. It's within W, okay? So if W has a dimension of n, for example, range of T can have a dimension bigger than n, okay? So if the dimension of W is less than the dimension of V, okay, that is that if W is a smaller space, right, in dimension-wise than V is, then the range can't possibly be the same size as V, okay? And if that's the case, that's where we get this. The dimension of V minus the dimension of the range of T is going to be greater than 0. Well, that means that the dimension of the kernel of T, right, by this equation right there, okay, has got to be greater than 0, okay? And so the kernel of T can't be just the trivial solution. It can't just be the 0 vector. It's got to be at least one vector or more, okay? So this idea here is that if V, or if W, is smaller than V, okay, then what we get is we get that the kernel of T cannot possibly be equal to the 0 vector, and hence T is not 1-to-1. So that gives me this conclusion. In order for T, okay, to be 1-to-1, the dimension of W, okay, must be greater than or equal to the dimension of V. Another way to actually think about this too is to think about it just in terms of numbers, and we'll use some examples. Let's say the dimension of V is going to equal 4, okay? And let's say the dimension of W equals 3. So 3 of the dimensions, okay, so we're going to take 3 dimensions in here, in V, are going to map onto non-zero values, at most, okay? And one of those dimensions has got to be that kernel of T, okay? And it's going to map onto the 0 vector here in the range, all right? If you think about it, we can only have so many dimensions in V mapping onto the same number of dimensions in W, okay? So the number of dimensions that we are taking in V that will map onto non-zero vectors, okay, is going to be the same size as the range, all right? And then everything else is going to be the kernel. So everything else inside of V is going to collapse down onto that 0 vector, right? So like say, for example, if we take 3 dimensions, right, in V, and they go over to the 3 dimensions in W, okay, we're going to have one more dimension in V, okay, and that dimension is then going to collapse down onto the 0 vector, right? Everything in that dimension goes to the 0 vector, right? Okay, so consequently, if V is bigger than W, okay, if V is bigger than W, that's the situation that we're going to have all the time. It might be 3, it might be 1, it might be 2, it might be 3, depending upon the size of the range, okay, but it's always going to be at least 1. And if you have at least one vector in the kernel, okay, it cannot possibly be the 0 vector. Our next idea is this idea of being onto. A transformation T v to W is onto if for all W belonging to W, there exists a V belonging to V such that T of V equals W, okay? So the idea here is that we have something in W, right, okay, anything in W, right? It's going to map back to something in V, right? Take a W1, it'll go to V1, right? W2, it'll go to V2, right? Choose anything in W, it's got something to map back to, right? There's nothing in W that can't actually be found with a what we call preimage in V, okay? And what that's equivalent to saying is that the transformation under my transformation T, the range of T is all of W, okay? The range of T is all of W. Basically, here's the idea, okay? I take anything inside of my codomain, okay? Anything inside of my codomain, I can get there using T. All right. Another way to think about that is the span of the column vectors of a matrix A, right, that goes along with T is going to end up being all of W. Okay. So the span of our column vectors is going to give me all of W, right? I can get anywhere in W. Yes. And what's that equivalent to? Well, that's the equivalent to, basically saying that the range of T is all of W, right? Because the range of T is the column space. Okay, so let's kind of think about that again. All right, I'm going to say that T is onto if every W in my codomain, right? All right, so my output space over here, okay, will map backwards to a V. That's basically equivalent to saying, right, that for every B belonging to W, AX equals B actually has a solution. Or if A is the matrix for T, right, then all the column vectors of A span W. All right. Okay, that's kind of like the idea, right? So the equivalent to that is to say that the transformation T, V into W, is onto if and only if the range of T is equal to W. So that's how we prove, right, that a transformation is in fact onto, is we show that its range is in fact all of W. Okay. Okay. So let's take a look, and we've got prove that T R4 onto R3 is onto. So what we want to show is that the range of T is equal to R3. And that's the equivalent of saying that the call space of A is equal to R3. Those two things are actually the same. So what I'm going to do is I'm going to row reduce and find the column space, or a basis for the column space. And if the basis for the column space has three vectors in R3, it's going to be R3. Hence, the range of T will be R3. Okay? Remember, these two things, they're basically equivalent. They're synonymous, okay, in many, many ways, all right? So I row reduce A, and when I take the RREF of A, okay, what's really important is that I end up with, and then I got something right here. Doesn't matter what's happening in that fourth one. This is what I end up getting, right? I have no rows of zeros, all right? I have no rows of zeros. Everything's inside of R3, okay? And I have these three vectors. So my basis for the call space of A is going to be the equivalence of where those three pivots are. And it's going to equal 1, 2, 1, 3, 1, 2, and 5, 2, 1. Okay? So the call space of A is equal to R3. Okay? We've got three vectors in R3. Okay? What is that? That's a basis for R3. So range of T equals R3. Okay? Thus, T is onto. Okay? Let's take a look at another example. Prove that T, P1 of X to R2, is not onto. All right, we're going to show that this one, in fact, is not onto. So we're going to take P1 of X, we're going to go into R2, okay? And this is going to be defined by A minus B and 2A minus 2B. And let's say that's going to end up equaling A equals 1, negative 1, 2, negative 2. Basically, that's going to be our matrix for the transformation when we transform our polynomials into vectors. Yeah, there you go. Okay. So A here, what we see here is that when we row reduce A, RREF of A, okay, we end up, that's going to equal 1, negative 1, 0, 0. Okay, right? The call space of A then is going to just equal basically the span, right? Or it's a basis for the call space is going to be the span of 1, 2, right? So the call space of A is only a one-dimensional subspace of R2. So call space of A does not equal R2. And consequently, because the call space of A doesn't equal R2, that means the range of T does not equal R2. So T is not onto. That's it. That's the idea. So let's talk about dimension and being onto. Now, let's suppose now that the dimension of W is greater than V. Okay, that the dimension of W is greater than V. Basically, our problem is going to be this. I'm going to take, this is, say, for example, the dimension of V is three-dimensional. Okay, dimension of V, excuse me, is 3. and the dimension of W, say, is equal to 5. Now these three dimensions, all three of them at best, okay, will map onto, so T will be able to map onto a three-dimensional subspace. Okay, and actually that even looks like it's too much. Let's say this much of it, okay? It's a 3D subspace. Because you can't actually add in dimensions, right? Means it's not a linear transformation if you actually add in more vectors, right? You can't add in vectors, all right? So consequently, what we've got is we've got a problem here, all right? For us to be onto, the dimension of V, okay, has to actually be bigger than the dimension of W, okay? We can, squeeze some of those vectors down into the zero vector like we did in the previous example with 1 to 1. That's okay, all right? But what we can't do is we can't expand out, right? And that becomes a problem with being onto, all right? So let's kind of look at this from a proof perspective. Suppose that the dimension of W is greater than the dimension of V. So we know that the range of T is contained within W. And so the dimension of the range of T is less than or equal to the dimension of W. Then by rank nullity, right, if the kernel of T equals 0, then 0 plus the dimension of range of T is equal to the dimension of V. So that's like your best case scenario, is that the kernel of T is 0. Okay, that's the best case scenario you've got here. Okay, then those two will actually end up being equal. All right, thus the dimension of the range of T is equal to the dimension of V. But we just said the dimension of W is greater than the dimension of V, so the range of T cannot equal W. Okay, it's not going to happen, right? So for T to be onto, the dimension of W has got to be less than or equal to the dimension of V, right? Okay, basically onto means that we can go from bigger into smaller. We can't go from smaller into bigger, okay? And being 1 to 1 means that you can go from smaller into bigger, but you can't go from bigger into smaller because something's going to collapse down onto the zero vector. So from a dimension standpoint, what if we wanted something to be both 1 to 1 and onto? On the one hand, okay, we showed that for T to be onto, the dimension of W had to be less than or equal to the dimension of V. And for T to be 1 to 1, the dimension of W had to be greater than or equal to the dimension of V. So for T to be 1 to 1 and onto, the dimension of V has to equal the dimension of W. Okay? So for a transformation to be both 1 to 1 and onto, the dimension of V and W have to in fact be the same. Okay, so this completes our conversation about 1 to 1 and onto. These are kind of some deep concepts. You probably have to think about them, read the notes a little bit. Also, you maybe go into your book and read some of the proofs in there, or take a look at the proofs that are on here. Okay, take some time to think about it. Proving that something's 1 to 1 and onto, no problem. Thinking about what it means to be 1 to 1 and onto, that's harder. Okay, and then also, what's the effect of being 1 to 1 and onto in terms of what does it mean for the dimensions of our domains and codomains? Okay, all right. So this completes our conversation.